to this first lecture in the series Probabilistic Verification. Well, first one remark, we are talking about verification of probabilistic systems, so the notion probabilistic verification is maybe not the right thing, because the verification, well, at least for my understanding, this would suggest that we talk about verification algorithms that are probabilistic, so it's the other way around. So one question which pops up rather natural would be, why do we need to talk about probabilistic systems? Well, and I think in computer science, probabilities, they play a role almost everywhere. So there is, for instance, the class of randomized algorithms, and both in the sequential and concurrent case, they often provide a very elegant way to come up with algorithms which might or might not be solvable also in the deterministic case, but then they are often much simpler, much easier, much more elegant, and sometimes also more efficient. Other areas, though, there is the stochastic control theory, operations research. That's another very traditional field where one considers typically some combination of probabilistic and non-deterministic systems. Performance modeling is also quite a prominent area where probabilistic models play a role historically. In this context, often one uses probabilities to specify some assumptions about the environment. Biological systems, then one often uses some kind of continuous time model, for instance, to describe the continuous evolution of some gene population, things like that. Or fault tolerance, to reason about the probabilities, the likelihood of failures, and so on. Now, when you want to analyze such probabilistic systems, then there are many types of models, and of course the analysis has to be specialized for the model you consider to come up with algorithms which really decide a verification problem. You need some assumptions on the model. This one thing is typically finite state, and the other thing is to use the Markovian property, Markovian models. And the meaning of this Markovian property is memoryless, so which states that when you have reached a certain state, then you can forget about the history. The future behavior only depends on the current state. Now, coming from standard classical automata, they have this, or one assumes this memoryless property as well. If you are in a state of a finite automaton, then you have certain outgoing edges, but then you can forget about what you have seen in the past. These are the options to take in this automaton. So it's the memoryless property. Here in the stochastic world, it also refers to the distributions you use on the model, but for the states, it's a rather natural assumption. To classify probabilistic models, there are various dimensions. Let's mention just two dimensions. There is the purely probabilistic case, so where we do not have non-determinism anymore, and there is the case where we combine probabilism plus non-determinism, and this is typically very crucial when modeling the interleaving of concurrent systems. And also for the probabilistic evolution over the time, you can distinguish between the discrete and the continuous setting. So in the discrete time setting, or this is often also the time abstract setting, a system just makes a step which is viewed as an atomic step, and you can consider it as one time unit or just as an abstract, in a time abstract way. Well, and in the continuous time world, you may assume that the time is represented by the reals, non-negative reals. Now, to fill this table, so the most prominent model here in the intersection discrete time, purely probabilistic, these are the discrete time Markov chains. We will come to this in a second. And here for when combining it with non-determinism, then the fundamental model is a Markov decision process which combines transition systems and Markov chains. Now here in the continuous world, the purely probabilistic continuous time, then the most prominent models are continuous time Markov chains, where you have exponential distributions specifying the delay of transitions. And here on this side, there are plenty of models that combine probabilism, non-determinism, and continuous time So there is a rather natural step going from Markov decision processes, so probabilism plus non-determinism plus exponential distributions. For the delay, this would give you the model of continuous time MDPs. Closely related are interactive Markov chains, but there are also completely different models like probabilistic timed automata, which is, if you're familiar with that, a timed automaton that where some edges can have probabilistic but discrete probabilistic behavior. Now in this tutorial, in all the 4 lectures, I will only consider here the discrete time case, and I will make the assumption that the given Markov chain or Markov decision process is finite. Well, we talk about verification on algorithmic verification, so this is the model checking schema. I think not precisely the picture, but in words, this appeared in Orna's talk. So we need some kind of operational model as the finite state representation of the system we want to analyze. And here on the right-hand side, we have some formalization of the properties. And then the purpose of a model checker is to do some computations and to come up with a correct answer, yes or no, the system satisfies or does not satisfy the specification. Now in the probabilistic world, the picture is similar, but here we want to reason about probabilities. Let's say the probability for some bad undesired behavior should be very small, or the probability for some liveness property, some good behavior, the how did you call it, the liveness? It was the finite waiting time, should be 1, or, I'm sorry for that, it is on my slides, it is full. Well, what is written here is instead of probabilities, you might also reason about some expectations, for instance, the expected costs until reaching a certain goal. Well, here are some historical remarks. So at least as far as I know, the very first work on verification of probabilistic programs goes back to Hartscharier and Pnöly in 1983, and they investigated the termination problem for probabilistic program, and here termination is understood almost surely with probability 1 does a concurrent program terminate. Well, and there is very popular work on linear time properties formalized in linear temporal logic, LTL, and the task to check whether a property holds with probability 1 or with positive probability. So this is meant by this word qualitative. This has been investigated in the mid-80s for discrete Markov chains and Markov decision processes. Well, and there was a short break, and I think once I asked Moshe what was the reason that in this time, so it's, if you look in the literature, there seems to be at the 90, there was almost nothing. And I think you gave me the answer. There were so many other interesting things to do. Well, for some reason, there was a bit a break. But then it was around 94, 95, where many people started to look again at this very fundamental work and to extend it in the direction of, for instance, some kind of branching time logic, probabilistic computation tree, or to extend this technique for continuous time models, or to talk about probabilistic timed automata, and so on. And nowadays there is a series of tools that support many types of models and many types of logics, and maybe the most prominent one is PRISM, developed at Birmingham and Oxford in the group of Marta Kwiatkowska. So this tutorial, altogether, I mean, not today, all the 4 lectures. We will first talk about the discrete time Markov chains. That's where we'll start with, and probably tomorrow, or I think so, tomorrow, we will start with Markov decision processes. So I guess we will stop here, but these are short. Well, the simplest way to explain what is a Markov chain is take a standard transition system or just a finite state automaton, and instead of having you are in a certain state and then you have a choice between different branches. Well, in this context, we don't care about the labels of these, just take it as abstract labels for the transitions. And any choice between alpha and beta is viewed to be non-deterministic, so not only two alpha edges. So you are in a state, then you have a non-deterministic choice between successors. Now, in the purely probabilistic setting, a Markov chain, we do not need these action labels. They do not play any role. You could attach them if you like. But the crucial feature is that we have, for each state, we have a distribution specifying the probabilities for the successor states. So in this picture, if you are in that state, then with probability 1/3, the system moves to this state on the left. Now, formally, the literature also considers infinite state Markov chains, but we suppose that the state space S is finite. This probabilistic evolution can be described by a matrix with rows and columns for each state. And so if you fix the first state S and you sum up the probability values when ranging here over the second state S prime, then you expect to get the value 1. So indeed, we would like to have a distribution for each state. And all these values are between 0 and 1, and not stated on that slide. When talking about algorithms, I suppose that these values here are rationals. To talk about temporal logics, you can attach atomic propositions or labelings to a Markov chain. You can declare certain states to be initial or to deal with an initial distribution that tells you what is the probability to start in each of the states. And you can augment such Markov chains with weights or rewards, which means that you can attach to each state or each transition some rational value. We will deal here with the case of integers or natural numbers. And there will be a difference for the algorithms. Well, here's a very simple example, a Markov chain with 4 states, which describes a very primitive communication protocol. So here we start and generate a message. Then we move to this state where the system tries to send the message. For some reason, something goes wrong, so the message gets lost via the channel with probability 0.02, in which case we try again, and we hope that eventually the message will be delivered and we return to the starting state. Now here, these are probability values specifying the behavior in this state try, and for all other transitions, if I skip any annotation, I mean probability 1. For atomic propositions, for instance, you might just look for the number of trials until delivered. Then you might decorate the starting state and this state message lost with an empty set, and this state with try, this with delivered. And for rewards, for instance, if you are interested in counting the number of trials, then you can attach your reward value 1 for this state try and 0 to all others. Now let's talk about the Sorry?
What do you mean? So I understand the reward on a particular state, but when you compute the reward along the entire state, you take into account the probability with which the reward might happen the next time?
We will come to this. Let's say we will talk about the accumulated reward along passes, and then you can talk about probabilities for events that refer, for instance, to the you want to reach something with some reward bound and then take the probability thereof. For the moment, this is just a definition. But I think there was another question, no? Okay, so let's talk now about the probability measure. So we suppose we have the Markov chain, the AP and L doesn't play any role, but we need an initial distribution. So just a function that tells us what is the probability to start in a certain state. Now the probability measure is a function that assigns values between 0 and 1, probabilities, to sets of passes, and they need to be measurable. And for this we need a sigma algebra. And the basic concept are here the cylinder sets, and let's start with this. So we take a finite path, and then by which I simply mean a sequence of states that you can get when taking edges in the underlying graph. Then the cylinder set means the set of all infinite paths that start with this particular prefix, and from then on you can continue in an arbitrary way. Now, here I said we deal with the sigma algebra, and if you look at some book on measure theory or probability theory, you will find a definition like this. A sigma algebra on some universe, on some set U, is simply a collection of subsets of U, which contains the full universe and which is closed under complement and countable unions and countable intersections. Now, here I said we take the sigma algebra, which is generated by the cylinder sets. This simply means that we deal with the smallest sigma algebra, where the universe is simply the set of all infinite paths, and the smallest sigma algebra that contains all the cylinder sets. Well, and then you can use results, well, these are not trivial results, but results that are known from measure theory. Here we use measure extension theorem by Kara-Theodori, stating that this sigma algebra fulfills certain axioms such that it suffices to define the probability measure of the cylinder set, and then you automatically get a probability measure for all the measurable events. Well, and the definition here is rather natural. We say the probability of such a cylinder set for the paths S0, S1 to Sn is simply what you would have done just by your intuition. We take the probability for starting in S0. So we take the initial distribution and we evaluate it for this starting state S0. So this is some value between 0 and 1. And then we multiply the probabilities of all the transitions that we take along this finite path, S0 to Sn. So just in case you never heard about sigma algebras and do not want to hear about sigma algebras, we talk here only in the discrete case, and there the good thing is just use your intuition. I'm sure you would do the same thing. Okay, let's look again for this example of before. Now we do not need to talk about rewards, we just look for probabilities. And the first event we consider is deliver the message within 5 or fewer steps. So we have just a single starting state, and there are 2 possibilities to deliver the message within 5 or fewer steps. Either we go from start to try to deliver directly, or from start to try to lost to try to delivered. So we have 2 cylinder sets generated or spent by this path start, try, delivered, or start, try, lost, try, delivered. Now, and we have here plus these cylinder sets are disjoint. So just plug in what is the probability for this one. Well, here we have 1 times 0.98, so we just get this value. And for this second pass here, we get this 0.98 multiplied with a 0.02. So altogether, we get this value. So this was for a step bound, and let's look now for the analogous thing, but without any step bound, just the probability to eventually deliver the message. We don't care about the number of trials. Well, again, you can do the same thing. What are the possibilities to deliver the message? Well, we start here, we go to trial, then we take this loop for a finite amount of time, let's say n times, and then we go to the delivered state. And the n can be any natural number. So here we have an infinite sum. Now you can plug in here the values for this, and what you would obtain, well, if you take this loop n times, then you get here probability 0.02 to the power of n, multiplied with this probability going from try to delivered. And this is a simple geometric series, and you just can plug in the formula you know for MET, and what you obtain is 1. which is also rather intuitive. Well, if you, let's say, if you toss a coin and you wait until head, on the long run, you will see it. Well, maybe there are exceptional behaviors where indeed you toss it infinitely often and you always get tail, but this appears only with probability 0. This is a legal path in this case, okay, but more or less in the probabilistic analysis we can rule out it because it occurs only with probability 0. Yeah, so here is again the definition of sigma algebras, and this is just to remind that we deal here with the sigma algebra generated by the cylinder sets. So let's look that these events we talked about are indeed measurable. So step-bounded reachability. We want to visit some set G within n of fewer steps. So we can indeed describe it as, in this case, in a finite union of cylinder sets. Namely, what we do is we take all the finite passes that end in some state of G, and we have here this step bound within n steps, so the finite passes up to length n. So this is in the end a finite union of cylinder sets, so it is measurable. We can even make sure that these here are disjoint by adding the constraint that none of these blue states belongs to G, because then we could stop already there. Well, then we have here again a finite union, and all these sets are disjoint, which means for the probability we can simply, this union becomes a sum. And you can do the analogous thing for eventually without any step bound. Then you can also, with this side constraint that none of the blue states belongs to G, then we also get here a sum, but now the sum is an infinite one. So let's look now for repeated reachability, infinitely often G. So like this Büchi condition in Gravier's talk. Here we can describe it, also as some Boolean combination, let's say some countable intersection of finite unions. And what we do here, infinitely often G, the idea to describe it as this set of infinite passes is, if some infinite path enjoys this property infinitely often G, then for all positions n, there is some position I greater or equal n where we visit a state in G. So that's the way you can read this formula here. Now in this case, there is no such simple formula just as a sum. You could here deal with some limit, but we will come, indeed it will be easy to compute probabilities for these events, but using not exactly this representation, using other observations. And these sets might or might not be disjoint. Well, and this is the dual persistence from some moment on continuously G. This is simply the complement of infinitely often not G, which means for the probability we can simply, if we know the probability for infinitely often not G, then we can simply calculate 1 minus to obtain the probability here. And one crucial thing, to compute this value here, one very fundamental and very simple property of finite Markov chains is the following. Whenever you have a finite state Markov chain, then what we can guarantee is with probability 1, a bottom strongly connected component will be reached and each of its states will be visited infinitely often. So formally this means the probability measure of the infinite passes such that there is some position I and a bottom strongly connected component C, such that from position I on we will continuously stay in C, and for each state S in C we will infinitely often visit S. And this holds with probability 1. Now here's a simple example. We have this Markov chain here, and there are two bottom strongly connected components, the red one and the green one. And well, here we have loops, as you have seen in this simple example, start, try, delivered again.
What are buttons strongly connected components?
I-
What does it mean?
Well, we consider just the graph, and then a strongly connected component is some maximal set where whenever you pick two states, they can reach each other via a path. And bottom means they have no transition outside, going out. So let's say here would be another strongly connected component, which is non-bottom because it has some transitions outside. Yeah? Well, and just to illustrate this statement here, if you start here in this initial state, then you might take this cycle here for a finite amount of time, or even go to this state and cycle here. But on the long run, you will make progress, let's say, towards some bottom strongly connected component. And this bottom property ensures that you stay there forever, because there is no transition outside. Yeah, so let's say these are the ingredients that will be very important when we talk about the computation of probabilities. Well, I will embed these algorithms, how to compute these probabilities, when talking about the model checking procedure for some temporal logic. And I will start with the full logic, PCTL star, explain its fragments, and then explain how to model check it. So in Orna's talk, you heard a bit about computation tree logic, not yet CTL star, which is the combination of CTL plus LTL. And here we talk about a probabilistic variant thereof, where we do not have these existential or universal path quantifiers. Instead, you have a probability operator to specify lower or upper probability bounds for temporal properties. We will later consider also not only probability but also expectation operators, but for the moment we leave them out. So here is the syntax. We distinguish between state and path formulas. And on the state formula level, we have propositional logic. And here the A stands for an atomic proposition. And so what we add here is the probability operator, P, which has two arguments. One is I, which is simply a probability interval, so an interval contained in the 0, 1. Well, not stated here. Typically, the requirement is that the interval bounds are rational numbers. And this phi here, this violet phi, is a path formula specifying a condition that a path might or might not satisfy. We come to this in a second. Just for these probability intervals, I mentioned before this notion qualitative properties. This is used for constraints where we say a certain formula holds with positive probability or holds almost surely, which means with probability 1. This is when we say that's a qualitative property, and quantitative means anything else. So, for instance, phi should hold with probability larger than 1/2. Let's turn now to the syntax of path formulas. So we also have propositional logic, but now the atoms are state formulas. So we can switch back and forth in this, generate state formulas using path formulas, and here we can use again state formulas. Well, this means we have the propositional logic fragment, and we have the next and the until operator that you have seen in Orna's talk. But did you talk about next? The X, yeah. Well, the X, well, I use the cycles and for the diamonds and boxes, but otherwise. And the until. And this, well, you had similar pictures in Orna's talk. So for the path formulas will be interpreted over infinite paths. And then we say a path formula satisfies such an state formula viewed as an atom on the path formula level, simply if the very first state satisfies phi. next A means that A holds in the second position and we don't care for the others, and until requires that the formula on the right-hand side will eventually hold and before A holds continuously. Derived, so Orner used an F for the finally, for the eventually. I use here the diamond operator. This is defined as true until B in this case, and the always operator, Orner used the G for that, is its dual. So always A means it is not the case that eventually not A holds.
You know how to remember which one is which?
The
The diamond is unstable equilibrium. It will eventually fall off.
Okay.
But the box is stable, it will stay there forever.
Okay. Good point. Okay. Yeah, for next. Because the diamond and box were already used. I don't know. So let's talk now about the semantics, and this is what I would say rather natural definition. So we interpret the state formulas over the states in a Markov chain and the path formulas over the infinite passes. So this is the semantics of the state formulas. Here, this is the propositional logic fragment, and here is no surprise. So for an atomic proposition, we just check the labeling of that state. And for instance, not phi holds for state S if it is not the case that S satisfies phi. Well, and for the probability operator, well, as I said before, the intuition is to specify that the probability for phi belongs to the probability interval I. So what we do is we take the probability measure of all the infinite passes starting in state S and satisfying phi, and we check whether this value, that's a value between 0 and 1, belongs to this interval I. If so, then we say S satisfies this state formula and otherwise not. Yeah, well, and for the path formulas, Anna, did you show this? Well, if you are familiar with LTL or CTL star, then it's exactly the same. In these pictures before, for the eventually and always operator, I gave you, or until I gave you an idea when the arguments of these formulas are atomic propositions. Now you can have nestings, you can have eventually always next A, which means that the argument of a formula with, for instance, the until operator, then phi 1 and phi 2, they can contain again temporal modalities, which means that in the general case, it doesn't make sense just to look for a single state when interpreting these sub-formulas. Instead, what we do is we say, let's look for the next operator, next phi holds, if the infinite suffix starting at the second state, this is now again an infinite path, satisfies the formula phi. So this, for instance, if the phi is again next A, then you can interpret this one, this infinite path over next A, and so it makes sense. And for the until operator, this is the analogous thing. You can keep this picture you saw in Orner's or in the previous slide in mind, but formally we need to go via the infinite suffixes starting at some position. Yeah?
I think the comparison with phi and L should not be strict. Q1 may still hold in the state L.
Yeah, it may hold, but it's not necessary that it holds. So these two conditions should hold, but I do not say that at position, if you consider the suffix here as starting at position L, I just say phi 2 should hold, but I don't say anything about phi 1. It could hold, but it's not necessary. Yeah, here are some examples for PCTL star specification. So again, for this simple example, for instance, you might require, or let's have this specification. It should hold with probability 1 that it is always the case when the system tries to send the message, then with high probability, with probability at least 0.9, the message should be delivered in the next state. Or this one here, with probability 1, when always the system tries to send the message, then it will be delivered eventually without returning to the starting state before. Or for some, just to provide another example, for a leader election protocol, for instance, you might want to have the property that indeed almost surely a leader will be elected. And with the ingredients you have seen so far, this is a not very elegant way to describe a step bound for the number of steps until a leader will be elected. So we have here a big disjunction and then sequences of the next operator. Later we will use a different syntax for that. So this would be the step bound. Within n or fewer steps, a leader should be elected, and then you might specify some probability value. So for the model checking problem, we are given a Markov chain and a PCTL star state formula, and this is just for simplicity. Suppose we have a unique initial state. Then, for instance, the task might be to check whether this unique initial state satisfies phi. So what we do is, in case you are familiar with that, with CTL or CTL star model checking, the general idea is the same, namely, we just go back to this recursive definition of the satisfaction relation, and more or less we just apply this definition algorithmically. So what we do is we evaluate inner formulas first, compute their satisfaction sets, which is defined as the set of states satisfying this considered subformula here called psi. And then as soon as we have computed the satisfaction set for the full formula phi, we can simply check whether S0 belongs to. Now this recursive computation of the satisfaction set, just go again to this definition of the satisfaction relation and rephrase it for the satisfaction sets. This is trivial for the propositional logic fragment, and it is also somehow trivial for the probability operator. The satisfaction set for this formula pi I phi is simply the set of all states S, where the probability for formula phi when starting in state S belongs to the probability interval I. So that's rather natural. But now we need algorithms to compute these probabilities, and this is now the more interesting case. And let's start with the special case where this path formula phi is a simple reachability condition. In that case, with this recursive computation of the satisfaction set of inner formulas, we can suppose that this state formula phi has been treated before, so we know its satisfaction set, which means that we deal here just with a reachability condition, reach some set of states. And to compute such reachability probabilities, the infinite state Markov chains, this is very simple, this can be solved using a linear equation system. And to illustrate this, I consider here a very prominent example which goes back to Donald Knuth. So this shows a Markov chain here, which can be seen as a formalization of an algorithm that simulates a six-sided dice by a simple coin, a simple fair coin. So the way to read this Markov chain is the protocol starts here in the initial state, then you toss the coin. If head, you go left, if tail, you go right in this picture. And eventually you will end up with one of the outcomes. Now let's verify that this algorithm or this Markov chain indeed does the job. So we want to have probability 1/6 for each of these outcomes. And let's just look for this state here, for this outcome 6, and let's verify that indeed the probability is 1/6. So the first observation is, in all these states here on the left, in this gray area, you cannot reach the outcome 6, which means if you say XS is the probability to reach outcome 6 from state S, so let's S be one of these states, then in all these cases the probability is simply 0. So we just have to deal with 4 states here. On the right, for them, we have a non-zero probability. The outcome 6 is again a trivial case. We already reached the target state, so the probability here is 1. So let's look now for these 3 states. What is the probability to reach the yellow state from the blue, green, or red state? Now for the blue state, x1, there is, with probability 1/2, we go to the left. But when we went to the left, then we cannot reach the 6 anymore. Then we know for free the probability from then on will be 0. So the only successful case is, which happens with probability 1/2, we move to the right. But then from that, so this is the factor 1/2, and then we multiply with the probability to reach the yellow state from the green one, which means we simply get x1 equals 1/2 x2. Now for the green state, you can do the analogous thing. With probability 1/2, we move to this area from which on we cannot reach the yellow state anymore. And with probability 1/2, we move to the red state, which gives us the probability for the green state is 1/2 multiplied with the probability for the red state. And for the red state, we have probability 1/2 to go directly to the goal state. This is this plus 1/2 on the right. And with probability 1/2, we go back to the green state. So altogether, we get x3 equals 1/2 x2 plus 1/2. Now, if you put these, let's say we have now 3 linear equations, and you can rephrase them, and this would be the analogous thing in matrix vector notations, and then indeed this one has a unique solution, and the solution is 1/6, 1/3, and in this case 2/3, and 1 here, which gives us indeed the desired result that this protocol does the job, at least for outcome 6, is obtained with probability 1/6. By symmetry, this also applies here to the left, to the outcome 1, and here you can do an analogous calculation.
One question. So what happens if this linear equation maybe have no solution of many solutions?
This cannot happen, not
by the definition of...
not by definition. Wait 1 second. Wait 1 second. This has to do with this pre-processing. I mentioned this gray area, and in the general case, what we do is we first filter out what are the states where the probability is 0, and this is not necessary to ensure the uniqueness of or an existence of a solution. Just for efficiency reasons, also you can filter out all the states where the probability holds with where the reachability probability is 1, which means that if we have here the full state space, here is the set of target states T, then we have here this blue area would be the S1, and here we have the states where the probability is 0, and in between this is what, in a second, what we will call the states where the probability is strictly between 0 and 1. Now these sets, they are easy to compute. The probability for such a reachability condition is 0 if and only if this state cannot reach a target state. There is no path from that state to reach the target state. Now for the probability to be 1, it's a little bit more complicated, but the infinite state Markov chains, it's also a simple graph analysis. Namely, what we can check is whether it is not the case that there is a path where we reach one of these states where the probability is 0, unless we have seen the target state before. So it is not the case that there is a path going to S0 without having visited T before. And in either case, you can compute them using a simple graph analysis in linear time. Now for the remaining states, these are all the states where the probability strictly lies between 0 and 1. This is the area S question mark. And this is the area where we use this linear equation system. And in general, the equation, well, what I've shown you for this dice example, then for each state in this area S question mark, we have an equation xs equals the sum, the weighted sum, so let's say the probability to move from S to S prime, multiplied with the probability for this reachability condition from S prime. And here we only consider the states in this area S question mark. For the states in S0, we can simply ignore them here. And for the states in S1, where we know the probability is 1, we can simply deal with the probability to go directly from S to such a state. Now, in the end, this last value here stands for the probability to move from state S to T via a path that, except for the first state, consists of states in S1. This one here, where we stay with the first transition inside this area in S question mark, stands for the other successful passes, which means from S we move to another state in S question mark, then we can stay in S question mark for a while, and then we move, eventually we move to S1. Now altogether, this one here gives in metrics vector notations. This means we deal with an equation of the form x equals ax plus b, and you can rephrase it in that way. If I means now the identity matrix, then this means I minus a times x equals b. And indeed, with this pre-processing, with this filtering out the states that cannot read the set S0, then this matrix is non-singular, which means it has a unique solution. This was exactly your question, right?
I mean, this should be a 0, right?
That's not, well, how to prove it that this is, you can,
The stochasticity of the matrix.
yeah.
This is a theorem in probability field.
Is this matrix nil%? Matrix A is nil%. If it is A, then this is I minus A must be regular matrix.
Well, I mean,
If the A is nil% matrix.
I learned this notion, but this is more than 20 or 30 years ago, and I forgot what nilpotent means. That's why I can't answer. Well, what I can say, a direct proof would be, you can immediately -1, the inverse of that. There is a formula, namely take the infinite series. It's a rather basic proof that there might be several arguments that can be applied. That's what I was saying. That's easier. Because we filtered out these states. This doesn't hold in general, not for any stochastic metrics, but because we have this S0 eliminated, then there are matrix norms where this one is less than 1, and then this one indeed converges, and what you can prove is that this is this one. I still have a few minutes. 5, okay. Okay, so this was just reachability, and let's look now for one fragment that we have almost finished. PCTL without the star. This means the sublogic of this full logic PCTL star, where on the path formula level we impose the following restrictions. We do not allow for Boolean combinations anymore, and we require that all the temporal modalities, next and until, their arguments must be state formulas. So let's say this would be as grammar, you can write it in that form. So you can still derive the eventually operator true until phi, and for the always operator, well, because we do not have the negation anymore on the path formula level, we cannot write it is defined by not eventually not phi, but we can use the duality of both lower and upper probability bounds and eventually and always, and to define, for instance, the probability for always phi is strictly less than 0.4 if and only if the probability for eventually not phi is strictly larger than 0.6. Well, and now for the model checking, we can do what I explained before for PCTL star, evaluate inner formulas first. And in this case, for the probability operator, again, we want to compute these probability values. And this means, well, I explained it for the eventually operator, but believe me, this can be easily adapted to treat the until operator. This is just this side constraint. You need to modify this linear equation system a little bit. And for this means that we can compute these values for the until operator using a linear equation system. And I didn't explain the next treatment of the next operator, but this is even simpler. This is just a single matrix vector multiplication, and then you can compare with the probability values here specified by I. So altogether, this gives that for the PCTL model checking, we have low time complexity, polynomial in the size of the Markov chain, and linear in the length of the given formula. This polynomial comes from these linear equation systems. Yeah, well, and what we do for PCTL star, again, this schema, but now we use this fundamental property of finite state Markov chains that I mentioned at the beginning, that on the long run, each infinite, almost all infinite passes will eventually enter a bottom strongly connected component. And so what we will do is, again, use some trick that is known also from the non-probabilistic case. With this, evaluate inner formulas first. We first can switch from a PCTL star path formula to an LTL formula, which means a formula that does not have any inner probability operators anymore. And then we can rely on an automata-based approach. I have here, yeah, well, just to sketch these ideas, first this step from a path formula of PCTL star to an LTL formula. Take this path formula here, the outermost operator is this eventually, and then we have this conjunction, here some formula and here some formula. Now with this recursive approach to evaluate inner formulas first, we would first evaluate these substate formulas with a probability operator. Then we compute somehow their satisfaction sets, and then we can simply do a syntactic replacement of this green and this rose formula with a fresh atomic proposition. So in the end, this would give us eventually A until D for this formula and always E. And now what we have here, this is now a proper LTL formula. We do not have nested probability operators anymore. Which means this is this step here from a PCTL star formula to an LTL formula. And then we use things that you have, that Javier, here you are, you did not explain today, but I guess from tomorrow on, there are algorithms that can generate a deterministic automaton from some LTL formula. Well, they have some acceptance condition. Suppose for simplicity, it is not the case. Well, I guess Javier will tell you more about this. It will be not a Büchi automaton, but for the moment, if you're not familiar with Rabin Street or so, just think of it as a Büchi automaton. Then the idea is to glue them together, the Markov chain and A, and then we get, again, a new Markov chain. And the reason why we deal here with a deterministic automaton is you can think of this product as a parallel composition. Now, but if this A is deterministic, then this just means we refine the information about the Markov chain, we add some information, but we do not influence any choices, and we can simply lift all the probabilities from the Markov chain to the product. And from then on, we can say the probability in the Markov chain for this formula phi equals the probability in the product to satisfy the acceptance condition of the automaton, which in the case of the Büchi condition would be a repeated reachability constraint, which again is reducible, and here we use this fundamental property of finite state Markov chains to a probabilistic reachability condition. So we have the probability to reach an accepting bottom strongly connected component. So altogether we have two steps, the graph analysis to compute the accepting bottom strongly connected components, and as soon as we have computed them, we can rely on this technique. I've shown you a linear equation system to compute the reachability probabilities. Now, which means that the time complexity for this part here is polynomial in the size of m and a. But here, being polynomial in the size of a is at the same time the problem, because here we can have a double exponential blow up, and there are examples where this is even not avoidable, independent of the algorithm you choose here. And Moshe is... may I mention this? Let's stop. Okay.
You're between them and lunch.
Good. Then I stop here.